Hi everyone and welcome back to NTE. In today's video we're going to be looking at the fertilizer industry, right? And basically what we're doing today really is more looking at the content behind the fertilizer industry, okay? It's a very small section that makes up physical science paper 2, right? So your chemistry paper. It's usually the last question in that paper, and if I were you, I would actually start with that question immediately when I receive my paper 2. Okay, very quick, 8 to 10 marks, maybe even possibly maximum 20 marks for you to just collect, right, and put in the bag and then carry on with all the other nitty gritty things about paper 2. Okay, right, so with that said, let's start with the video. Okay, right, so the fertilizer industry, basically, they are going to test you on just knowing where do the fertilizers come from, right? So how do we actually manufacture the fertilizers? And that is going to draw from the knowledge that we've already accumulated from the previous sections, right? Mainly the section of chemical equilibrium, right? Where we looked at the Haber process, we looked at the contact process, we also looked at the Oswald process, right? So they're going to want to know those processes, right? They're going to ask you just general questions about that, okay? And then one of the biggest things in the fertilizer industry as well is just knowing how to read something called the NPK ratio, right? And how to use that to calculate, for instance, the mass of nitrogen in a fertilizer bag, right? And we'll get to that, right? Other than that, really, most of the other content in this section is more for general knowledge and just to help you as a person, right, to be informed about what happens in the real world, okay? It also helps you to just get a sense of, if maybe let's say you want to go into agriculture and you want to become a farmer, right? What are the implications of using fertilizers? Why do you need fertilizers and all of that? Okay. All right. So in general, right, we can say that the rise of fertilizers, okay, was basically brought about by the increase in world population, right? So as the world population kept increasing over the years, right, there came a point where governments had to find a way to support their nation, right? And obviously, people need to eat, okay? So the normal way of farming couldn't sustain, right, the large growth in population, okay? So then, you know, scientists had to come up with ways, right, chemists actually had to come up with ways of how do we produce a substance that will help us to grow plants at a faster rate, right, in order to meet this large growth in population. And that's where the invention of fertilizers actually came about, okay? And it all started off with Fritz Haber actually discovering how to change nitrogen, which is in the air, right, and hydrogen through, we know this from chemical equilibrium, right, using that whole process of fractional distillation, right, and converting those two key and very simple molecules, right, nitrogen and hydrogen, into ammonia, right? And then from there, as they say, the rest is history. Okay. Now we say that plants, okay, just like humans, right? Plants need minerals in order to function and grow. Okay. Now there's important minerals that plants need to get specifically from the groundwater that is in the soil. Okay. So there's some minerals that plants need to have that they can't get just from the atmosphere. Okay, so we say that, okay, in the atmosphere, right? So if we just look at this little picture of my plant over here, okay, in the atmosphere, the plants can get things that we call non-mineral nutrients. Okay, so those are your things like your carbon, your hydrogen, and your oxygen. Okay, so plants can get those minerals from just the surrounding air, right? That's fine. But there's certain things that plants need, right, that they need to grab from the water, okay, or from the soil, right? And those nutrients are the nutrients that we are actually focusing on in this section of fertilizer industry, right? And those are actually called the primary nutrients of plants. Okay. All right. Okay, so now we need to note that as more and more of the nutrients, right, which are actually taken up by the plants, right, as more and more of those nutrients actually are used by the plants, right, the soil becomes leached, or what we call depleted of nutrients. Okay, so thus it becomes important for us to actually return these nutrients back into the soil, right, so that we can carry on harvesting, right. So organic fertilizers such as manure, right, uh, bone meal, okay, and wood ash, right, don't actually replace these nutrients fast enough, okay, in order to support a large world population. Okay, farmers like to say organic fertilizers feed the soil, right? So they restore the soil back into its natural state where it's able to actually perform well and it's nice and thick and moist and everything, right? Whereas artificial fertilizers, which is what we are creating as humans, right, in order to sustain commercial farming, right, artificial fertilizers, farmers say that those actually just feed the plant, right, and they feed the plant just for that specific time, right, and most of the time it's even too much for the plant to actually intake. Okay, so yeah, it's a win and lose situation. We need organic fertilizers to have healthy soil, but then at the same time we need artificial fertilizers in order to feed a large population. Okay. Okay, so before we carry on, let's just remind ourselves, why does a plant, okay, need these non-mineral nutrients? Well, it needs the non-mineral nutrients in order to undergo the process of photosynthesis. Okay. Now remember that photosynthesis is the process that plants use, okay, in order to produce glucose for themselves, right, which is one of the ingredients that they need, okay, in order to produce ATP, or their energy molecule. Okay, so basically it's their way of actually producing energy for themselves. They store the glucose in form of starch, and you eat the plant, and then you then get that energy. Okay, right? And if we just remind ourselves of the equation for photosynthesis, right, we know that we are going to need carbon dioxide, okay, which obviously the plant takes in from the atmosphere, okay, and then it also then needs water, okay, which the plant basically just draws, okay, from underground right through its roots, okay, and this simple reaction produces glucose, C6H12O6, okay, plus oxygen. Okay, and this oxygen is basically what the plant then releases into the atmosphere so that we can breathe. Right, so this right over here is just extra information if you would like to just remind yourself, okay, but it's obviously not something that we're going to focus on for exam purposes. Okay. Right, so now let's move on to talk more in depth about plant nutrients. Okay, so we have already said that plants actually need nutrients in order to function and grow, right? And they take these nutrients from the soil, right? Okay, so we further divide these nutrients into primary and secondary nutrients, right? So the primary nutrients are the nutrients that the plants need in large amounts, okay? The secondary nutrients are nutrients that plants need but in smaller amounts, okay? Right, so now we are basically going to be focusing on the primary nutrients, okay? So the primary nutrients is nitrogen, phosphorus, and potassium, okay, or what we are going to more commonly just refer to as NPK, okay. Right, and then the secondary nutrients is your calcium, your magnesium, and your sulfur. Right. So now we're going to talk more about these primary nutrients. Right, we're going to talk about just one of their functions, okay, and then we're also going to look at their sources, right? So both the organic source and the artificial source of all these three nutrients. Okay. Why do plants need nitrogen? Okay, well, plants basically need nitrogen in order for them to be able to grow healthy leaves. Okay, right. So we say over here, right, that the function of nitrogen is primarily for leaf growth, right? But in fact, nitrogen in a plant is responsible for this entire, right, above the ground growth. Okay, so this entire part of the plant that is above the ground, okay, that is stimulated and promoted by the presence of nitrogen. Okay, and the reason why it can do that is because the plant also uses the nitrogen, okay, in order to produce proteins and enzymes. Okay, and obviously proteins and enzymes are two key components, right, for anything to grow. Okay, right. Now, what about the sources of nitrogen? What is the organic source of nitrogen, right? So before we started using fertilizers, what did farmers use that actually contained nitrogen? Well, farmers used manure, okay, in order to get nitrogen to the plant, right? And manure is basically just animal droppings and anything that has decomposed, right? You can create organic manure for yourself, right? Like I said, using vegetable peelings, right, and eggshells and stuff like that. So as soon as those things have decomposed, they basically form this mushy soil type of thing, okay, and that is called manure, right? And some of you might have come across the smell of manure. It's not the prettiest smell in the world, or the most pleasant smell in the world. Okay, but now what about the inorganic or the artificial sources of nitrogen? Well, those are going to come from our fertilizers, right? And those are just going to be nitrogen-based fertilizers, right? So in our nitrogen-based fertilizers, we have things like, I'm just going to name two of them here, right? So things like ammonium, sorry, right? So ammonium nitrate, okay, that is a artificial fertilizer, and basically this ammonium ion is highly soluble in water. Okay, so that is how the plant gets nitrogen artificially, or you can also talk about something like ammonium sulfate. Right, and we're going to look more at these fertilizers later on as well. Okay, so we're going to just put this function of nitrogen onto our diagram, right, and state that nitrogen basically promotes healthy leaf growth. Okay, now on to phosphorus, right? So phosphorus, okay, for plants, phosphorus main function, okay, is to stimulate root growth. Okay, so what is an example of an organic source of phosphorus? Well, phosphorus is found organically, right, in something that they used to call bone meal, right? So that's just crushed up bones, right? And then you just add that into the soil. Okay, right. And then what about the artificial source of phosphorus? Well, the artificial source of phosphorus comes from a very important rock, right, that is mined, right? And that rock is called ferroapatite, okay? And it has a ridiculous equation, right, that you don't really need to know, right? But basically, the rock ferroapatite, okay, is reacted with sulfuric acid or with phosphoric acid, right? And then it creates a substance called superphosphates, right? Now, superphosphate is a substance that can also be added into fertilizers, and that will be the artificial source of phosphorus for your plants, okay? Okay, so if you want to do a little bit of research for yourself, right, about the artificial source of phosphorus, then just research this substance, ferroapatite. Okay, so this is a mineral that's mined, right? It's found within a rock, obviously, and it is actually mined in South Africa as well, right? It's mined in Limpopo, right? Okay, so we then need to add this into our sketch again, okay, and we're going to add it right over here, okay, all over here for the root system, okay, we need phosphorus. Okay, so phosphorus, you need to remember, basically just stimulates root growth. Okay, so basically without the phosphorus, the plant has no chance whatsoever, okay, because it has to start off with its roots before it can show up on the outside as well. Okay. Right, last one, potassium. Right, so what is the main function of potassium? Well, the main function of potassium is to improve the quality of the flowers and the fruit in the plant. Okay, so for example, with this plant that we have over here, it's got flowers and also has fruit. Okay, you can see it right over here. Okay, we've got some fruits over there, we've got some flowers, right? So those two things are basically promoted and sustained by the presence of the nutrient potassium. Okay. So something else that potassium does is that it actually supports photosynthesis, okay, and it also helps to make the plant more resistant to heat, drought, and any diseases. Okay, so it makes it sort of like temperature resistant. Okay, phosphorus also actually makes the plant resistant to certain diseases. Okay, so you can see how important these nutrients are to the plant. Okay. Okay, so now let's move on to talking about what is the organic source of potassium. Well, organically, potassium is found from wood ash. Okay, now artificially, plants get potassium from fertilizers as well. Okay, and they will get the potassium from any potassium ion containing salt, right? So things like potassium nitrate, or maybe even potassium sulfate. Okay, so these salts that actually contain the potassium plus iron, okay, that will be the artificial source of potassium for your plants. Okay. Okay, so we've spoken now about the primary nutrients of the plant, okay, and we've also looked at what are the organic sources of those nutrients and what are the artificial sources of those nutrients, okay. So now we're going to focus more on these artificial sources of the nutrients, right? Well, basically what we're now focusing on is the artificial fertilizers, okay. Now, when we have fertilizer, okay, we just basically create a mixture of ammonium sulfate, ammonium phosphate, ammonium nitrate, potassium chloride, and the superphosphates that we talked about. And here is that ridiculously scary looking formula, right, for that represents the superphosphates. Okay, if we just go back, right, remember that the superphosphates were the artificial source of phosphorus, okay, for the plant, right? when we take those components and we mix them in together with what we call filler material, right? So that's things like just normal soil, okay, sand and some limestone, okay. When you mix all of that together, right, then you create artificial fertilizers, okay. So these final products right over here, right, the ones that we've listed at the top, okay, these ones, unfortunately, we have to produce them, okay. That's the word artificial, okay. Right, so this is where your examiners are going to focus, right? So you are basically going to need to know in some way, okay, find a way for yourselves to remember how do you end up with these fertilizers over here, okay. And we know that the ammonia, right, came from the Haber process, right, and the nitric acid came from the Oswald process. Okay, we're going to remind ourselves of these two processes in due time as well. Okay, again, if you're looking at ammonium sulfates, right, you see again you've got the ammonia, right, so that's from the Haber process reacting with sulfuric acid, right, and that is from the contact process, right. If you take ammonia and you react it with the weak acid phosphoric acid, right, you get ammonium phosphate, okay. The ammonia will come from the Haber process, and in the phosphoric acid, you don't really need to know where do we actually get that, okay. And then lastly, you can have nitric acid reacting with potassium chloride, okay, to give you potassium nitrate, okay. Right, so just to fix something over here, instead of potassium chloride there as one of the things that we mix in to make artificial fertilizer, it's actually potassium nitrate. Okay, all right, so yet again the nitric acid will come from the Oswald process, okay, and you don't need to know where do we get the potassium chloride, okay, but you can imagine that could come from, that's a salt, right, so that could come from just a simple acid-base reaction, okay. Further on in the fertilizer industry, you're going to be required to know how to read, right, something called a NPK ratio, right. Now this is something that you're just going to have to remember, that this ratio is always in the order N, P, and K, right? So the N is nitrogen, the P is phosphorus, and the K is potassium, right? Makes sense because this is also just the elemental symbols of these three substances, okay? Right. Now, I was doing a little bit of research and I realized that there is some sort of a lie that I've heard my teachers say previously, okay? So normally you will read in your textbook or you will hear your teacher say that after this NPK ratio, right, you should have something in brackets, right, some number in brackets, okay, and that number must represent or represents the percentage fertilizer in the bag, okay. So in this bag, we've got a mixture of things, right? Some of it is actual fertilizer and some of it is just something we call fillers, okay? So soil and sand and limestone, okay? Right, so the textbooks will say that what is inside this bracket, okay, is actually shown on the packaging, okay? So I was looking for a lot of packaging for fertilizers and I realized that they don't actually put any number in brackets on the actual packaging of fertilizer, okay. So that kind of makes sense. I can understand why they wouldn't do that. It's sort of like a marketing strategy, right? Why would you want to display on your packaging what percentage of what's inside of this bag is actual fertilizer, okay. But anyway, that is just me just pointing out that I found that when I was actually looking at real life packaging of fertilizer, I didn't see any number in brackets. Okay, there's nothing, like you can see over here, there's nothing in brackets, right? But the NPK ratio is displayed quite clearly. Okay, right. So we are now going to then focus and say that, well, for our exams, okay, we are going to have given to us some sort of NPK ratio, and what is in the brackets, right? So that number in the brackets, you need to know that is telling you the percent fertilizer, okay? So that will make sense when you do an example, right? And I'm going to use this example to basically illustrate what all of this means, okay? Right, so we're going to summarize this by simply saying that for our exam purposes, okay, we are always going to be given some NPK ratio and some value inside of brackets, right? So there's going to be a value inside over here, okay? And we need to understand that this value inside of the brackets is telling us the percentage of fertilizer, okay? Right. One of the main questions that they will ask you is to figure out what is the mass, right, of nitrogen in this fertilizer, what is the mass of phosphorus, and what is the mass of potassium. Okay, so the way that we go about that, there's two ways that you can go about it. Is that you can first calculate what is 20% of this mass, okay, and then obviously then that will give you the mass of fertilizer from this total mass, okay, and then from there just calculate using these ratios, right, the mass of your nitrogen, potassium, and phosphorus. Okay, another way to do it is to say, okay, let me first calculate the percentages. Okay, so I'm going to show you how to do that version. Okay, I'm just going to erase this verses over here. Okay, so you would say that, well, the first thing I want to do is to calculate the percentage of each nutrient. Okay, so basically moving on from there, you would say that, well, I want to calculate, okay, what is the percentage of nitrogen in this bag, okay, and you can do that by using the ratio, right? You can say this is going to be equals to 4 out of 11, okay, parts of this total percentage of fertilizer, okay, so times 25. Okay, so when you do that on your calculator, right, you get that, I'm going to round it off to 2 decimal places, right, 9.09%, okay, is actually nitrogen, right? And when you add up these percentages, okay, you'll see that they actually add up to this total percentage of fertilizer, which is 25%. Okay, right, so that is basically you doing the first step, which is calculating the percentage of each nutrient. Okay, and then you would go over, right, I'm going to carry on here at the top, right, you would then go on and answer whatever question they're asking you. Okay, so for example, maybe let's say they're asking you what is the mass of nitrogen in the fertilizer. Let's actually do all of them. What is the mass of phosphorus, and what is the mass of potassium? Okay, then that is just going to be simply using these percentages, right? So you now know that 9.09% of this total mass, okay, 22.68, that will give you the mass of nitrogen, right? And that works out to be 2.06 kilograms. And that's obviously going to be the same as the mass of potassium because it's in the same percentage. Okay, and then the mass of phosphorus is going to be the 0.82% times the total mass, 22.68. Right, and that gives you 1.55 kilograms if you round it off to 2 decimal places. Okay, but and then when we add these up, okay, so these values, we get that the total mass of fertilizer, okay, is 5.67 kilograms. Right, so I'm pretty sure you could have come to that same answer by just evaluating the mass of fertilizer, okay, by using this percentage, 25% of the total mass. And that also works out to 5.67 kilograms. Okay, so yeah, that is basically the two steps that you can take. Right, so your first step would be, when you're given this NPK ratio, right, to calculate the percentage of each nitrogen, each nutrient, okay, right, and that is using the ratios, and just remembering that this denominator, right, so this denominator of 11, okay, that is just the sum of all of these numbers over here in the ratio. Okay, so 4 plus 3 plus 4 gives you 11 parts. Okay, so that's where the 11 comes from. Okay, when you're calculating these percentages, right? And then from there you then calculate, depending on what the question is asking you, the mass of the nitrogen or the mass of the phosphorus or the mass of the potassium, okay, and the sum of those masses will then give you the mass of the fertilizer. Okay, right, so going back to this step over here, right, we noted that these fertilizers, okay, actually have to be produced, right, and the raw material that is needed comes from other processes, right, so the Haber process, the Oswald process, and the contact process, right, so that's things that we need to know. Okay, so we are now going to remind ourselves about the Haber process, the Oswald process, and the contact process. We're not going to look at it in as much detail as what we do in chemical equilibrium, but we're just going to quickly have a refresher of all the equations, temperatures, and catalysts that we need for each of these processes, okay, because that is also something that your examiners are going to draw from, okay, for the fertilizer industry. Okay, right, so let's begin with your Haber process. Okay, right, so we see over here we already have the equation for the Haber process, right? We've got nitrogen plus hydrogen giving you ammonia, okay? And this is in fact nitrogen gas, right, plus hydrogen gas giving you liquid ammonia, right, which you can see right over there. Okay, ammonia outlet, okay, the ammonia is cooled down, right, and we collect it as a liquid. Okay, it's produced as a gas, but we collect it as a liquid. Okay, right, again we know that the enthalpy for this reaction is negative, telling us that this forward reaction, remember that this is in equilibrium, okay, that the forward reaction is exothermic. Right, and here they've listed for you different Kc values, right, for this reaction, and remember that we already calculated in a previous video this specific Kc value for the Haber process at 400 degrees Celsius. Okay, you can go have a look at that video just to see how did we go about doing that. Okay, right, Well, we just need to remind ourselves that this process has to occur at a temperature range, okay, of about between 400 to 450 degrees Celsius, right? Some textbooks say between 400 to 500 degrees Celsius, right? So that is what we called the compensation temperature range, right? So that we are balancing out both Le Chatelier's principle and the reaction rate. Okay, so remember that because this is an exothermic reaction, okay, as they note over here in this little box, okay, in order for you to maximize the yield of ammonia, right, which if you go back here, you can see ammonia is a very key component, right? We see it showing up in 3 of these reactions, okay, that form our fertilizer, okay. So you definitely want to increase the yield of ammonia, right? So now, because this is an exothermic reaction, Le Chatelier's principle tells us that we need to lower the temperature, okay, but then we can't use temperatures that are so low, okay, just for the benefit of increasing the yield of ammonia, right? Because then the reaction rate becomes too slow, right? We can't wait that long in order for us to produce the ammonia, right? So what we do is that we compensate, right? So we compensate by using a little bit of a higher temperature, right, which is also optimum for the catalyst that we use for this reaction, so that we can increase the reaction rate. Okay, so let's just note down what is that catalyst that we use in this process. Okay, so the catalyst that we use in this process is iron, okay, or iron oxide. All right, what about the pressure? Well, the pressure has to be 200 atmospheres. Okay, now this is just direct application of Le Chatelier's principle, right? We use this high pressure, okay, because then it promotes the forward reaction, okay, because for the forward reaction we only have 2 gas molecules compared to the 4 gas molecules on the right hand side, left hand side. Okay, right. Right, so let's just quickly look at this diagram. Right, you can see we have ammonia and nitrogen coming in. Right, so the inlet, it flows down this tube and then it goes down. Right, when it goes up over here, right, it gets in contact with these coils, right, and they say over here that that is to preheat, okay, the gases, right. So the gases are preheated, okay, and then they go past, right, the iron catalyst, right, which is shown over here in this green part, okay. After going past that iron catalyst, they will obviously then react, and at this point what is coming out here is nitrogen, hydrogen and ammonia gas, right? That goes through this heat converter up the tube, um, then it comes down in here right into this gas cooling chamber, right? And then basically this just cools down the ammonia only, okay, and then the ammonia goes into the liquid phase and then we collect it, right? And then any unreacted, right, so unreacted nitrogen and hydrogen, that is then recycled, right, then goes back that way. Okay, it will then go through here and then back down again and start the process all over again. Okay. Right, so now let's move on to the Oswald process. Okay, so remember, what are we producing in the Oswald process? We are producing nitric acid, okay, as indicated on the diagram over here, right? And specifically, we get dilute nitric acid, but we get nitric acid nonetheless. Okay, right, so remember that for the Oswald process, we've got 3 different steps, right? And I just want to correct over here. right? This second step is in equilibrium. Okay, so there's an equilibrium that is established between the nitrogen monoxide gas with the oxygen gas and the nitrogen dioxide gas. Okay, right. So that is also something very important for you to remember, that the second step of the Oswald process is an equilibrium reaction. Right. So we don't necessarily need to know what the names of all of these reactors and components are, right? We just need to know the reactions that are involved, right? The three reactions that are involved in the Oswald process. Okay, right. So let's start off with the first one. Okay, so for the first one, we see, okay, ammonia reacting with air, right? And we are going to have an excess of air, right? Um, Basically, the ammonia is actually reacting with the oxygen in the air, okay? And this is over a catalyst, right? And that catalyst is platinum, right? At a temperature of about 900 degrees Celsius, right? So that's going to produce our nitrogen monoxide. So that is the product over here, nitrogen monoxide, okay? Now, the nitrogen monoxide then goes into the second part of this reaction system, okay? But it then establishes an equilibrium with oxygen gas, right, to form nitrogen dioxide, okay? So basically, if we follow these arrows, right, this is the nitrogen monoxide that is coming into this area, okay? In this area, since we had excess air, we have excess oxygen, right? That is where it's then going to react further with the oxygen to form nitrogen dioxide. Okay, so now the nitrogen dioxide is what's going to go through this final part. Okay, now if they ask you, maybe let's say they put this reaction in a chemical equilibrium question, remember that nitrogen monoxide is a colorless gas, okay, and nitrogen dioxide is brown in color, right? So if maybe let's say they put this in chemical equilibrium and they tell you that they do something to disturb this equilibrium, right, and they want to know what is the color of that reaction, if it favors the forward reaction, then the reaction vessel or flask or whatever will be brown in color, right? And if it favors the reverse reaction, it will be colorless. Okay, right. So then the nitrogen dioxide then goes and it then goes into this absorption tower, right, where it gets absorbed into this water, right, that is being sprayed into this tower. Okay, so the nitrogen dioxide is coming in through here. Okay, it's then going to rise, okay, because it's a gas, and as it's rising it gets absorbed into the water, right, to form the dilute nitric acid. Okay, and there is the dilute nitric acid right over there. Okay, something else that is formed when we produce this nitric acid is we also form nitrogen oxide again. Okay, now this nitrogen oxide can then be recycled back into the system, right? So we can have recycled nitrogen monoxide back into this second step, right? Out over here is going to be any waste gases. Okay, so like that water vapor that was produced here in the first step. Okay, it can then go out over there, right? Okay, so we just also need to add on to this, right, the pressure at which the Oswald process occurs, right? So the Oswald process occurs at a pressure of plus minus 1 atmosphere, okay, which is actually quite a safe pressure if you compare it to the pressure that we need in order to conduct the Haber process, right, which is 200 atmospheres, okay. Right. Right, so the last process that we need to remind ourselves about is the contact process, right? And the contact process is the one that we use, very small diagram over here, we use to produce sulfuric acid. Okay, again, this is also divided into 3 steps, right? Where the second step is also in equilibrium, right? Or a equilibrium reaction, okay? So the first step is right over here. Okay, so we've got solid sulfur, right, which is burnt, okay, and that produces sulfur dioxide gas. Right, so that sulfur dioxide together with some excess oxygen, okay, that then flows into the converter, right, where it's going to meet the catalyst of this reaction, okay, and the catalyst of this reaction is vanadium pentoxide. Okay, right, so this is the one that establishes equilibrium, right? So we're going to have the sulfur dioxide gas reacting with oxygen again, right, over the vanadium pentoxide catalyst, right, at a temperature of about 450 degrees Celsius, right? The pressure is 5 to 7 atmospheres, okay, and this then produces sulfur trioxide gas. Okay, and the delta H for this reaction is also less than 0. Okay, telling you that the forward reaction is exothermic. Okay, and there is the sulfur trioxide coming out of the converter over here. Okay, now similar to what happened in the Oswald process, right, where we had the nitrogen dioxide going into an absorption chamber, right, where it got in contact with water, right, which is being added into this. Okay, a similar thing happens over here, right? Instead of adding in water at this stage, okay, what we add in is concentrated sulfuric acid. Okay, so coming in over here, it's very small in writing. Okay, we've got some concentrated sulfuric acid coming in. Okay, the reason why we don't immediately add the water is because if we add the water immediately right now, okay, we're going to form a fine mist which is very toxic and dangerous. Okay, so what we do instead is that we take the sulfur trioxide gas, right, and we allow it to be absorbed in about 98% of sulfuric acid, right, and that forms a super concentrated form of sulfuric acid that we call oleum. Okay, it's got this formula, H2S2O7. Okay, so this over here, this is called oleum, right? And I actually lied to you because we actually have a fourth step, okay, where we now dilute the oleum. Okay, so we take the oleum and we dilute it. Okay, so we add some water to it right there in that step. Okay, and then that just gives us 2 moles of sulfuric acid. Right. Right, so that is the 3 processes that we use, okay, to produce our raw materials for the fertilizers, right? Haber process for the ammonia, Oswald process for the nitric acid, and the contact process for the sulfuric acid. Okay, and then from there we then use those raw materials together with each other or together with something else like phosphoric acid or potassium chloride to form these 3 or 4 fertilizers. Okay, the most important ones being these two over here. Okay, so these two reactions, okay, of how to produce the artificial fertilizers, these two are actually going to be examined. Okay. Right, so just to round everything up, right, we also need to then talk about the impact of over fertilization, right, is something that you need to know as a responsible citizen. Okay, right. So basically, these fertilizers that we produce, okay, so these artificial fertilizers that we produce, those are highly soluble in water, okay, and they have to be soluble in water because when we go back to this slide, right, we said that where was it, our plants, right, they absorb, right, their important nutrients, okay, from the water, okay, in the soil, right. So they obviously have to be highly soluble so that they can be in the water that the plants absorb. Right, so now sometimes it can happen that the land actually becomes over fertilized. Okay, so you put so much fertilizer into the land that not all of it is used up by the plants. Okay, so now those soluble nutrients, right, specifically the nitrates and the phosphates, okay, they then leach, right, or basically go into the groundwater, right, and they find their way into streams, rivers, lakes, and seas, right, um, either through the groundwater or through surface runoff, right? So when it rains, okay, and it actually passes through that over fertilized land, okay, those soluble nutrients then get absorbed into the rainwater, right? And the rainwater also ends up in your streams, rivers, lakes, seas, and dams. Okay, that is called surface runoff. Okay, right. So once these nutrients, right, actually end up in these areas, okay, it's not a good thing, right? Because then what happens is that they result in eutrophication. Okay, and eutrophication is basically displayed in these two images over here, right? You don't need to know in detail how does that process occur, right? But you can imagine if fertilizers are used, okay, to actually promote the production of crops, right? We use it to promote more crops growing, okay? When that ends up in your rivers and lakes, right, it's going to promote your plant material that is in those rivers and lakes to grow as well, okay? And actually, the problem with this is that it causes a drastic, very drastic, right, increase in plants called algae, right? And these are these green plants that you're seeing on the surface of the water over here, right? So when that algae overgrows, right, we say that we now have an algae bloom, okay? It's not a good thing. It's not a pretty sight either, okay? So now you can see that when it blooms, right, it basically covers the entire surface of your stream or your lake or whatever water source it's in. Okay, it's actually going to block, right, the sunlight from coming through. Right, so the sunlight is not going to come through anymore. Right, so which means that any other organism or plant that is within the water that is dependent on the sunlight, right, to actually undergo photosynthesis, that is not going to occur because it can't access that sunlight. Okay, that's basically going to mean that if it can't undergo photosynthesis, it can't make food for itself and it will die. Okay, right, so when all of these organisms actually start dying, right, they then need to decompose, right, which needs bacteria, right? So bacteria actually promotes the decomposition of dead matter, okay? Now, when the bacteria decomposes the dead matter, it uses up oxygen, right? The process of decomposition uses up oxygen, okay? So, which further decreases the oxygen supply in the water, okay? Now that leads, right, to the water becoming deoxygenated. Okay. So now nothing can grow or live in deoxygenated water. Okay, so you can see that over here we've got a poor fish that has died because of eutrophication. Okay, now water or eutrophic water, right, is now toxic and absolutely unusable. Right, so over-fertilization is not the only cause of eutrophication, right? Stock breeding also contributes to eutrophication, maybe not to such an extent as over-fertilizing, okay? But it contributes to eutrophication based on the fact that animal waste, okay, can also act as a fertilizer, okay? All right, so now before we actually end off this video, I want to go back to the harbor process. Okay, right, and I just want to talk about or note, okay, the sources of nitrogen and hydrogen. Okay, so the hydrogen, we said that we're talking about the sources over here. Okay, we said the nitrogen comes from the air, right, and we get it through fractional distillation. Right, so now what about the hydrogen gas? Well, that is produced through something called coal gasification. Right, and that's basically just blowing hot steam right over some coal. Right, so the coal is in the solid form, and then you just blow hot steam, okay, over it, and that will give you the hydrogen gas and some carbon dioxide. Okay, so yeah, okay. So this is one of the processes that happens at SASOL, okay, amongst a lot of things that happen at SASOL. Okay, um, let's go to the Oswald process. Let's talk about the sources over here as well. Okay, so the ammonia is obviously coming from the Haber process, and the oxygen, okay, is coming from the air from fractional distillation as well. Okay, and then lastly, what about the sources of the contact process? Well, for the contact process, we need to start off with sulfur, so that comes from sulfur. Okay, and then we also have oxygen, okay, that is coming from the air. Right. So basically, this process of fractional distillation is all about just separating the nitrogen and the hydrogen from liquid air, right, using their boiling points, right. The compounds that have a lower boiling point, which between nitrogen and oxygen is actually the nitrogen, right, those ones actually evaporate first, right, and are collected up top, right? And then the rest of the other gases that are actually in that liquefied air, right, such as your oxygen and your argon, those are then going to follow, right? Right, so then that's it for the fertilizer industry, right? We're basically just talking about where do these primary nutrients, right, that plants need, where do those actually come from?